Hey, good morning, everyone. Hope you had a good weekend. Today, we are going to be moving on from our discrete time population models that we were looking at up until now to continuous time models. And pretty much the rest of the course will be focusing on continuous time models. First of all, in one dimension, for just a simple homogeneous population, so there's no variation in that population. And then we'll be moving on to think about structured models where there's variation. So that could be different species, or it could be different ages, or different sexes. So we're going to be starting off thinking about how we construct these models, going from discrete time to continuous time, and then seeing what the exponential and logistic growth models look like when they're in this format. Okay. So by the end of the day, today, you should be able to understand what it means to have a continuous time models and when we should be applying them, and how we can construct them from first principles. Okay, so like I said, so far we've only modeled time in discrete steps, okay, whether these are days, weeks, months, years, generations. You start off with a population at a particular time point, and then you're projecting forward over a given projection interval to the population at another time point, but you don't know anything about what goes on in between, okay? And in many cases, that is a reasonable approach to take, and we use difference equations or recursion equations to model those populations. But in some cases, it's not a great way of doing things. And also there are more mathematical tools that allow us to work with continuous time models a little bit better. So we're going to think about how we can construct these continuous time models. So rather than just having these integer values of time, so day 1, day 2, day 3, and so on, we're going to have t as just any non-negative real number. In fact, it can be the negative value, but we're going to keep it as being something that's non-negative. Okay, so first question then is, when might it be more? When might a model in continuous time be more appropriate than one in discrete time? Any ideas? Yeah.
Like a model can't be, there's not like fixed time periods.
Yeah.
So the likelihood is being like this, like.
So can anyone remember what that is right yet? Can anyone remember any of like the reasons as to why we would choose a discrete time model? Like biological reasons about the population itself. Yeah.
I think one was like the population.
Yeah, so if there's some kind of like strong seasonal effects, right, where say most of the births or most of the deaths occur in a short period of time, then you want to account for some of that synchronicity. And so, yeah, making these projections forwards is kind of makes sense. But in many populations, births and deaths happen throughout the year or whatever. And those models, they do kind of account for that, but they're kind of averaging over that period as well. So not having that seasonality, we can actually incorporate seasonality in continuous time models as well. You can have things like your birth function as a sine wave. So it will peak at some points and it'll be low at other points. But typically, we tend to think about using continuous time model when we have things that occur that are not well sort of synchronized in time. So, e.g., births and deaths are non-seasonal. Okay, so let's think about the first model. If you recall, the first model we looked at was an exponential growth model in discrete time. So this is where we had our population at the next time point, n sub t plus 1 is equal to our current population size nt plus some births and some deaths, or subtracting some deaths. And then we wrote this as nt times by 1 plus b minus d, or just lambda nt, where lambda is a constant. So we refer to B and D as our per capita birth and death rates. So you can think about those as being the number of births and deaths that occur in 1 unit of time, or rather B times by NT. So let me just edit this a little bit here. BNT and DNT are the number of births and deaths that occur in 1 unit of time. So B and D are the rates, but B times by NT is the number. So if we want to convert this into a continuous time model, how do we do that? Well, first, there's a little bit of a change of a notation. When we're in continuous time, rather than writing n sub t, we have n brackets of t. So n is a function of t. So that's the population size or density of the population at time t, and this is a continuous variable now. And what we want to do is we want to now think about what is the population size at time n t plus delta t, where delta t is some small time step in the future. Okay, so if we think about time running along a line, we have our population at time t, and then we have a population at time t plus delta t. So we can start off by thinking about this as our discrete time model. In our discrete time model, this delta t was just equal to 1, right? We're just going from n at time t to n at time t plus 1. Now we're going to say, rather than having this fixed interval, we're going to set it to some small interval delta t. So in this window, we have bn of t times by delta t births. And we have d times by n of t delta t deaths. Like I said before, we had delta t was just equal to 1 in our discrete time models. Okay. So now we're having an arbitrary window. So what is our population going to be at n t plus delta t? That's going to be n at time t, so the current population size, plus what? What should I write next? So n times by delta t times by what? Not sure. It's okay. So before we had n at time t plus 1 in discrete time is equal to the population at time t plus bnt minus dnt. So plus births minus deaths. So now rather than having this delta t equal to 1, we're going to generalize it. So now we have, this is our number of births and this is our number of deaths. So what do I write here for our plus? So we have n at time t plus what? bnt delta t, yeah. And then what else do I need to add onto this?
Yeah.
The deaths. So minus d n of t delta t. So this is directly analogous to this, right? What I've done is I've replaced that plus 1, or rather in the top up here, I have delta t is equal to 1 in this line here, and I've generalized it to any time window I want. Okay? Does that make sense? Okay, so let's do a little bit of rearranging. The first thing I'm going to do is I'm going to subtract n of t from both sides. So n times t plus delta t minus n of t. What else can I do? I'm going to take out a factor of n of t here and delta t. So this means I can write this as b minus d times by n of t times by delta t. Okay, that's just doing a little bit of algebra to rearrange that. And then the last thing I'm going to do is I'm going to divide both sides by this delta t. So if I divide both sides by delta t, it goes away from here and arrives down there. Okay, so up until now, this is still in discrete time. I just have an arbitrary window of length delta t. Now I'm going to take the limit as delta t gets smaller and smaller. Okay, so as delta t tends towards 0. And as it tends towards 0, the left-hand side, we turn into our derivative. Okay. Now we have dn of t with respect to t, dt, is going to equal what? Well, in fact, I'm going to write this line up here as r times by nt. So this is equal to rnt, where r is equal to b minus t. Okay. So we can see that the link between the continuous and the discrete time model is all we're doing is we're just setting ourselves up as having an arbitrary window length, an arbitrary projection interval. And then we're going to make that projection interval smaller and smaller and smaller until we end up with our derivative. And this gives us an instantaneous rate of change at any value of time t. And typically as well, from now on, rather than writing out n as a function of t, n of t, we'll just write n. Okay. Okay. So when we have simple models like this, we can actually use separation of variables to solve this. Does anyone remember separation of variables and integration as to how we would solve this? I see a nod or two. Okay. So how do we do that? Well, we had the n dt is equal to Rn. That was what we had before. I've just dropped the t's in brackets. So if we divide both sides by n and do the separation of variables with our dn and our dt, we can write this as the indefinite integral of 1 over n with respect to n is equal to the indefinite integral of r with respect to t. Does that make sense what I did there, or does anyone have any questions about what I've done? I assume silence is, you're fine with that. Okay, so now we just need to integrate both sides. So what do we have on the left-hand side, anyone? Natural log of n, yeah. And what do we have on the right-hand side? RT plus constant, yeah. Well done for remembering the constant. We don't need to put a constant on the left-hand side as well, because if we put a constant on each side, say C1 and C2, we can just combine those two on one side. Okay, so that's why there's no constant on the left-hand side. Okay, we want to have this as a function of n. So we can take exponentials. So we can have n at time t is going to equal e rt plus c. It's the exponential of rt plus c, which we can write as e to the rt times by e to the c. And c, since c is just a number, we can write this as, say, some constant a multiplied by e to the rt, where a is equal to e to the power c. They're just numbers, so we can just replace them to make it a little bit simpler, okay? So this is why we have exponential growth, because we have an exponential in our solution. If this is an initial value problem, if we have an initial population size, n0, then we can find the value of this constant. So n0 has to be equal to our population at time 0. So in our solution, we're going to have a e to the 0, which is just going to equal to a. So that tells me that my solution, n at time t, is going to equal my initial population size times by the exponential of r times by t. So, yes. As in the integrals, where they come first. As in going from here to here. Yeah, so this is using separation of variables as a technique to integrate. Okay, so if you're not familiar with separation of variables, I won't go through it now as to like where this all comes from, but have a look at that online, and it should hopefully be fairly straightforward. It's a way of, if you've got a relatively straightforward differential equation like this, you can split the variables up. It's pretty rare that you're able to do this. Most of the time, you're not going to be able to split things up. This is one of the rare cases where you can do it, and that means you can write down an explicit solution. In many cases, we won't be able to write down an explicit solution. Okay, so if you remember before, when we looked at our discrete time models, we were able to summarize the behavior. So before we had, in discrete time, n at time t was equal to our initial population size times by lambda, which was our growth rate, our net growth rate, to the power of t. Okay, so we thought about values of lambda that tell us whether the population is going to grow or decay. So how would you summarize the behavior of the model above, this one here that I'll circle in red, depending on the parameter r? So like, when does this grow and when does it decay? You look like you're about to. Yeah.
It grows when R is greater than 0.
Yep. So if r is greater than 0, then we're going to be having an exponential of something positive times by t as t gets very, very big. Then we see that n of t tends towards infinity as t tends towards infinity. And conversely, anyone else, when does it decay? When r is negative. If r is less than 0, n of t tends towards 0 as t tends towards infinity. Can anyone tell me what happens if r is equal to 0? Yeah.
Like the population stays the same.
Yeah. So r is equal to our births minus our deaths, or our rates. So if births are equal to deaths, there's no change in the population. Okay. So if r is equal to 0, n of t is equal to n0, our initial population for all t. Okay, so we've got the discrete time version above with the lambdas in. So how does this compare? Well, let's think of our discrete version and our we've just shown that it grows when r is greater than 0 and decays when r is less than 0 in continuous time. Can anyone remember what the conditions were in discrete time? That's for this equation up here. When does this one grow? Yeah. Lambda's greater than 1. And when does it decay? Someone else? I don't want to pick on people, but yes. So when lambda is less than 1, and we usually say it's greater than 0 as well. So we see here that although they are very, very similar models, with this is geometric growth, you can convert it into exponential growth. And here we've got true exponential growth in continuous time. The thresholds are different in discrete and continuous time. Okay, so depending on which version of model you're working with, you're thinking about, is this population growing or decaying? Make sure you remember that the threshold switches when we go from discrete to continuous time. Okay, let's think about our logistic growth model now. So in continuous time, we write this as dn dt is equal to Rn times by 1 minus n over k. Well, once again, we have R being our intrinsic growth rate. So what happens in the absence of any density-dependent effects. And K is, again, our carrying capacity. So just as when we had our nonlinear discrete time models, just as a reminder, this exponential growth one here is a linear model. It either just grows off to infinity or it decays to zero. When we have a density dependent version, we can have steady states or equilibria. And we can find whether the population is going to tend towards those or whether it's going to move away from them. Okay, just the same sort of argument. We also had previously in discrete time whether things would oscillate as well. So how do things differ when we're in continuous time? Well, our equilibria, n star, are going to satisfy f of n star is equal to 0 now. So this is my f of n. Previously, in discrete time, can anyone remember what our condition for a steady state was? If we had n plus 1 is equal to f of n, can anyone remember what the condition for stability was? Sorry, condition for a steady state. We'll go with stability in a second. That's for the stability. Well, how about just finding the steady states? Yes, we have, in this case here, let me just move it down here. So for a steady state, we needed to have n star is equal to f of n star. So here we have f of n star now equal to 0 rather than being equal to n star. And now also we have that an equilibrium here is going to be stable if the derivative, we still do the same process. We take our f of n, we take the derivative with respect to n, and then we see what the value is at each of our equilibrium points. If the derivative is now negative, then it's stable. And if it's positive, then it's unstable. And those are the only two outcomes that you can get. It's either stable or it's unstable in one dimension. If we think about how this compares to the discrete time case, well, we can write the conditions in a slightly different way as to what we had before. We said it was stable if our derivative of our growth function evaluated our steady state. We take the absolute value of that. If that's less than 1, then it was stable. If it was greater than 1, then it was unstable. But we also had a second condition. It's oscillatory if f prime of n star was negative. So can anyone tell me what some of the differences are between these two things? What's the most obvious, biggest qualitative difference between the continuous time stability and the discrete time stability? Okay, what are the two things that can happen to stability if it's in continuous time? Yep.
Converges to a steady state or diverges away.
Yep. So that steady state is either stable or unstable, right? Those are the only two things that can happen. In discrete time, we can have it being stable or unstable, but what else can also happen? Yeah, so it can be oscillatory stable, it can be oscillatory unstable, it can be monotonic stable, monotonic unstable, okay? So in continuous time, we'll have no oscillations. Come back to that. The reason why is because when we have, let me zoom in close here so I can sketch something. When we had our, say, our discrete time model, this was our time, this is our population size n. Suppose we had some steady state like this. In discrete time, we make these jumps, maybe it looks like this. If that gray dashed line was stable, if it was an attractor, we've overshot it now. So then we would undershoot it when we come back. Then we overshoot it, undershoot it. Maybe we tend there in the end, but Either way, we're oscillating about it, right? Whereas when we're in continuous time, we don't have this undershooting and overshooting situation. If we're in continuous time, because our change is instantaneous, we would approach like this. So if we compare that to the discrete time case, if I join these dots up, we'd oscillate around, maybe tend towards it, maybe not tend towards it, but we don't have that overshooting, undershooting situation when we're in continuous time. Okay, an exercise for you guys to practice finding stability, finding steady states and stability. So I'll just write down the logistic growth model again. dNdt is equal to Rn times by 1 minus n over k. So f of n. And we have steady states or equilibria are when f of n star is equal to 0. And then stability is stable if f prime of n star is negative. Just incidentally, before going on, the reason for this is exactly the same process as we did in discrete time. So we have a nonlinear model. Remember, like the surface of the Earth, something that is curved. It's nonlinear, but if you zoom in enough, it looks linear. So we make exactly the same arguments about a small perturbation, and then we see whether that small perturbation grows or decays. We're doing exactly the same things we did in discrete time. Now we're in continuous time, and that the perturbation grows according to an exponential. So it either grows as e to the lambda t, with lambda being positive, or it decays as e to the lambda t, with lambda being negative. So does that perturbation grow or decay? Depends on exactly the same setup as we had before in discrete time. The only difference is now the boundary is shifted and we don't have these oscillations. Okay. So have a go with this equation here. Find the equilibria of this logistic growth model, and then analyze the stability of those equilibria. Does anyone not know what they need to do? Whilst we're just waiting for the last couple of people to finish. Being able to find, like if I was to give you a population model, find equilibria, find stability, whether that's in continuous or discrete time, that's the kind of thing I'd expect you to be able to do on, say, one of the quizzes or in an exam, okay? So make sure you're familiar with this process. Okay, so equilibria, we need to set, I'll tell you what, I'll do it on a new slide. So equilibria n star when f of n star is equal to 0. So when does that occur? Well, we just set the right-hand side of this equation up here equal to 0. So we have Rn star times by 1 minus n star over k must equal 0. So just like before, we essentially have some number here times by some number here. That must equal 0. So either the bit outside the brackets or the bit within the brackets must be equal to 0. So this tells me that either Rn star must equal 0. If R is positive, then n star must equal 0. Or 1 minus n star over k must equal 0. Means that n star must equal k. And just as before, we refer to this first one, n star is equal to 0, as being an extinction or trivial equilibrium. Trivial because everyone's dead, then nothing happens. Whereas here, this n star is equal to k, this is our carrying capacity, or non-trivial equilibrium. And note as well about this idea of being an equilibrium. This is a dynamic equilibrium, right? You've still got births coming into the population, you've still got deaths going out. So there's still turnover within that population. It's just the population size isn't changing. You can think of this as like having a bath, and you've got the tap flowing water into the bath. So there's a constant stream of water coming in, but you've also got the drain letting water out, and those two things are balanced. So the rate at which water is flowing in is balanced by the rate at which water is flowing out, and then the level of the water isn't changing. Okay, so that level of the water would be your carrying capacity, would be your population size. That's the sense of the dynamic equilibrium. Okay, so that's the equilibria, and then let's think about our stability. So someone remind me what I need to do to find, what's the first thing I need to do to find stability of these equilibria? Yeah. Yeah, take the derivative of, yeah. So find f prime of n is going to be r times by 1 minus 2n over k. And then we think about what happens at each of our equilibria. So when n is equal to 0, we just substitute this in. The bit in the brackets is going to go to 0, or rather it's going to go to 1. This bit will go to 0. So this is going to be equal to r. So this is stable if r is positive, and unstable if r is negative. How about at the carrying capacity? Now we're going to have r times by 1 minus 2k over k. So the k's will cancel. You have 1 minus 2 in the brackets, so that's going to be minus 1. So we just end up with minus r. So this is just going to be the opposite. Stable if, slightly annoying on my screen, so I'm just going to have to move that. Stable if r is positive, and unstable if r is negative. Okay. So we talked about bifurcations the other day. Can anyone tell me what kind of bifurcation happens and when? It's just the same as when we had our discrete time models. Maybe the first question I'll ask, I'll come back to you in a second. Maybe the first question I'll ask is, when does a bifurcation occur? At what value of r? Anyone? Someone else who hasn't answered something before? Okay. I'm gonna pick on you.
I just had a question. So
Okay.
are we saying that if r is greater than 0, both nodes are stable?
Oh, my apologies. Sorry, I meant to write it the other way around. Thank you. Apologies if that was causing confusion. That should have been, this trivial equilibrium is stable if r is negative, and unstable if r is positive. Sorry if that was causing a few confused looks then. Okay, given that it's now correct, can anyone tell me where a bifurcation occurs? Remember, a bifurcation is all about some change in the stability. So when is there a change in the stability? What value of r? At 0? Yeah. So usually when I'm asking questions, they're not trick questions, like 99% of the time, okay? But it's kind of boring if I just stand up here. It's making sure that you guys are actually understanding what I'm saying, and I haven't written anything stupid. So there's a bifurcation at r is equal to 0. Can anyone remember what were the two types of bifurcations that we had in our discrete time models? Can anyone remember the names of them? There's a period doubling bifurcation and a transcritical bifurcation, yeah? Can anyone tell me what type of bifurcation this is going to be? Transcritical, and why is that?
The sign or like the stability changes depending the sign.
Yeah, so the key thing with a transcritical bifurcation is you've got two equilibria, or two steady states in discrete time. You've got these two equilibria. One of them isn't coming into existence or being annihilated or anything like that. They both exist as you pass through this bifurcation parameter, but they're stability switches. Okay, so R is 0. This one goes from being stable to unstable, and this one goes from being unstable to stable. Okay, any questions about anything we've gone through today? Abhishek fans who's met in any of their previous courses a continuous time model like this, the logistic model, or something similar? 1, 2, kind of, maybe? Did anyone cover this? Did you cover this in 260? We can't remember because it was a month ago. Okay. So this kind of logistic growth model is one of the most basic and most common forms of incorporating density dependence. It was the same in discrete time as it is in continuous time for the same reasons. It's very widely used. You only need these two parameters. As before, when we did the discrete time version, we derived these parameters. They didn't just get like the carrying capacity wasn't just plucked out of thin air, and the intrinsic growth rate wasn't. These depend on density dependent and independent death rates, as well as the birth rate. Okay, so the same logic applies here. I just haven't gone through all of that from basics. But they can be used to describe anything from tumor growth to rabbits. Eventually there's a depletion of resources, which is why this rate decays, the growth rate decays, and it ends up with some carrying capacity. So yeah, if you were to sketch this, you can actually find the solution to this model. If you were to sketch it, it ends up looking something like this. So we have time, we have our population. In fact, I sketched it earlier. But you end up with an S-shaped curve like this. So very early on, you have exponential growth. But as the population grows, this starts being reduced. So those density dependent effects reduce population growth until eventually the population saturates at its carrying capacity, K. If you increase R, what would happen to this green curve? Any ideas? If I increase the intrinsic growth rate of the population, what's going to happen? Is it going to move up, down, left, right? Exactly, yeah. So if you increase the intrinsic growth rate, it still has the same carrying capacity, right? We haven't changed any of our, just 1 second. We haven't changed any thing about our equilibria, right? We still have n star is 0, n star is k, but the rate at which we're going there is faster. So let's say this is R big. Sorry, you had a question.
So these would be for positive R. If it was a negative R, it'd be like your.
If it was negative R, it would just decay down. So if I do, so this is all R positive. Very briefly, if we had R smaller, it would look something like this. Okay. Question about if R is negative. Let me find another place I can sketch it up here. There we go. So if R is negative, what would it look like? Well, here, I'm going to start it off at a larger value. Say I'm up here. Now it will be, if this is my N0, now the population will be decreasing. It won't go negative. Oh, a bit of lag there. It won't go negative, but the population will decrease. Good question. Okay, we're a little bit early today, but I'll hang around for a few minutes in case you have any questions about this or other material. If not, you are free to go. Oh, one quick question. One quick thing. Sorry, I think there's a slight mistake in the self-study problem, so I'll correct that and then post it online. So when I post all the materials online, I'll correct that as well. So don't have a go at that until I've corrected it because I think it's a mistake in it. Okay. Other than that, yeah, you're free to go.